lecture, we will discuss Fisher discriminant analysis. With principal component analysis, we try to find out the vectors where the variance of the samples are maximized. Also, we project our samples on axes that are in the direction of those vectors. Whereas, that method might not help us with the classification problem we have. Fisher discriminant analysis, or linear discriminant analysis in general, helps us with projecting the samples on the best possible axes in order to linearly separate them. For instance, when we have such labeled data of two classes, we can, using principal component analysis, we can project them in the direction of the highest variance. However, that projection does not help with separating data. With linear discriminant analysis or Fisher discriminant analysis, we can maximize the distance between the means of the groups, as well as we maximize the variance in the line that the samples are projected. So we can have this projection line, and we can easily separate the samples after projecting them on this line. For Fisher discriminant analysis, we construct a set of objective functions and then combine them in order to find the axis that not only maximizes the difference between the class means, but also maximizes the variance or scatter of the samples that belong to each class. So, for two classes, let us have n1 samples from the first class and n2 samples from the second class. We estimate the class means of our samples as mu1 is the summation of samples belongs to the first class divided by number of samples. Similarly, mu2 is the summation of samples belong to second class divided by n2. Now suppose that we use a linear transformation to project any sample in the direction of a vector w, such that this w is this vector, and the projected samples are the points on this vector. So the projected samples are y, that is equal to w transpose times x for each sample, and the projected mean of the class labels, so we first project them on this line and calculate the mean of each class here and here on the projection line. So projected means of the class labels mu1 tilde and mu2 tilde will then be the average of y, the projected points that belongs to the first class, and mu2 tilde belongs to the first class. That's equal to w transpose x, where x belongs to the first class, and that's equal to w transpose times average of x that belongs to the first class, that is from here, that's mu1. So we have mu1 tilde to be equal to w transpose times mu1. Similarly, we can calculate mu2 tilde. Now, we can define an objective function that can be used to maximize the distance between the estimated means of the class labels. So, this shouldn't be estimated but projected. Okay. Projected means of the class labels. So if we take the difference between these class labels and we try to maximize them, we can have an objective function. So that's equal to w transpose times mu1 minus mu2, since we have them here. One problem with the objective function in the equation tree is that it does not take the variations within classes into account. As we have mentioned before, we would like to project our samples along a line which also maximizes the variance within each class. So when we look at these distributions for example, distribution of first class and second class, we can see that this axis can better separate these classes. However, this axis contributes to a larger distance between the means. So, there's a better axis for projection than both of these x1 and x2 axes, which is this line. If we project all of the samples on this line, we can easily separate them here. Also, we can have the variance of the samples that is largest. Therefore, Fisher defined scatter for each class in order to measure within-class variance of the class labels to normalize the objective function in the equation 3. So that's equal to y minus mu I tilde square is defined to be s squared. And the new objective function proposed by Fisher is mu1 minus mu2 squared divided by s1 tilde square plus s2 tilde square. Using the previously stated relations, we can represent the measure si square in terms of w. So, since si square is defined to be y minus mu tilde I square, we can have that y equals w transpose x from here, and also we can have mu I w transpose times mu I tilde equals w transpose times mu I, and when we square this part and we take w out, we have w transpose w and x minus mu I times x minus mu I transpose. And we can call this part of the equation Si, where Si is defined to be the scatter matrix of the samples that belongs to class omega I. Using the scatter matrices S1 and S2, we can define the total within class scatter, which is the sum of them, and simplify the normalization term of the Fisher objective function as follows. So we try to simplify this term. Since we defined SW that's equal to S1 plus S2, and we know that Si is double transpose Si times W, we have double transpose Si times W, S1 times W, double transpose S2 times W, and we just sum them up and have this expression. Now we need to transform the denominator of the Fisher objective functions to a function of W in order to optimize by using W. We already know that mu1 minus mu2 is W transpose mu1 minus v2. When we take the square of the both sides, we have W transpose mu1 minus mu2, mu1 minus mu2 transpose W. And here we defined SP, we defined this part of the equation to be SP, and the equation 7 becomes W transpose SP times W. Finally, we can express the Fisher objective function in terms of W, SW, and SP. So the lower part of the equation becomes, so upper part of the equation becomes this, and the lower part of the equation becomes this. And in order to find the maximum of the objective function JW, we can differentiate it and equate it to 0. So we have the differential of the division here, differential of derivative of this term multiplied by this term, minus derivative of this term multiplied by this term and divided by square of this term here. So we equate it to 0 and we just discard this term from the equation and divide the both sides with W transpose SWW and we get this expression. Note that this expression here is our objective function, and we know that this objective function evaluates to a scalar. So we can replace that part here with a term, let's call it lambda, that represents a scalar value, and this turns equation 10 into a generalized eigenvalue problem here. Assuming SW has full rank matrix, that means it has an inverse, we can convert equation 11 into a standard eigenvalue problem by multiplying each term with inverse of the SW. So we have W equals inverse of SW times mu1 minus mu2. With W we reach our line of projection. We can calculate W transpose X for any of our samples in order to find the projected samples. For example, let's say that we have 5 samples of our first class, omega 1, and 6 samples of our second class, omega 2, here. When we represent them on the Cartesian coordinates, we have these from our first class and from our second class. Note that when we use PCA in order to project them, we have this projection, which does not help at all with classification of these samples. Now, for Fisher-Linear discriminant, we prepare our data in 2 matrices. Let's call it omega 1 and omega 2 matrices. And we can compute the means of these matrices along the direction of sample dimensions. And we get the mean of the first class as 3 and 3.6, and we get the mean of the second class as 3.3 and 2. So we get the mean of this row, this column here. We get the mean of this column here. Similarly, for the second class, we use samples from the second class. Now we can compute the scatter matrices for each class. So for each sample, we subtract the mean from that sample and multiply by itself, transposed, and sum them up. So we get scatter matrices for each class like this. Now we calculate SW, that's within class scatter, by adding them up. And when we take the inverse of it, we get this. Finally, we can calculate the optimal projection, optimal line direction. That's easy. Just multiply this with mu1 minus mu2. We already calculated those here. And we achieve our projection line. Now we can project our samples to this line to get the transformation. So for the first point of the first class, we have projected a point on the line W, just W transpose X, which is our first sample, this one, in order to get the value of the projected point on the line W. Computing the projection for all points will give us a nicely separated set of samples from the both classes. Note that the position of the line does not matter, only its direction matters. Only its direction matters. So instead of this line here, we can have a line that's parallel to it, and the projections won't be changed, and that will be equally useful. So note that when we project our points to this plane, this line, we get all the samples are separated, and we have the distance between the class means well separated as well. So this is all for the dimensional reduction methods for this class, but note that there are other dimensional reduction methods, for example, mutual information, analysis of variance, also we can use support vector machine ways. These are also useful dimensional reduction methods. Also we have independent component analysis. These are also useful dimensional reduction methods, but we don't cover them in this lecture. Thank you for listening. See you next week.